Okay, let me first thank the organizers for giving me the opportunity to describe our work here. So I am a senior research associate at Satyendranath Bose Institute. So the title of my today's talk is Local Unidentifiability, a novel quantum non-locality and its application in security tasks. So our work is basically based on this particular archive paper. We just put that paper last year, and it is still now in communication. So I did this work with 3 of our collaborators. Pratik Ghoshal is basically a PhD student at Bose Institute. Orthogonal Ghoshal is now doing his postdoc at IMSC. He will be obtaining his PhD degree very soon. And Shumendu Ghosh is a PhD student at ISI Kolkata. So the plan of the talk is like that. I will first very briefly introduce the idea of quantum non-locality and also local indistinguishability. And then I will move to new quantum non-locality, which is coined as local unmarkability. And then I will move to our work and then its application, and at the end, the conclusion. So quantum non-locality is basically of two kinds. The first one is Bell non-locality, which says that there is no local realistic explanation of some outcome statistics from bipartite input-output experiments. And it was first introduced by John Bell in 1964. And we all know that last year, these 3 experimenters, Alain Aspect, John Clauser, and Anton Zeilinger, awarded the Nobel Prize for their works of experimentally verifying the violation of Bell inequalities. But today we will not talk about this Bell non-locality. Today's topic is local indistinguishability and the development on these. So local indistinguishability is not actually Bell non-locality. And in the next slides, I will very briefly describe about this. So let us consider that there is a referee and 2 players, Alice and Bob, who are basically spatially separated or may not be spatially separated. So initially, the referee has a set of orthogonal bipartite states. So it is here, psi1, psi2, and ... psi(n) up to psi(n). So the referee will choose one particular quantum state from this set, and it will be shared between Alice and Bob. Alice and Bob doesn't know what particular state has been chosen by the referee. Their task, Alice and Bob's task, is basically to perfectly recognize the state. So this question is basically twofold, or you may say the scenario is basically twofold. It may happen that Alice and Bob are situated in a same lab, just like that. So both of them has accession of both the 2 subsystems. So as a result, they are allowed to perform global or joint measurement on the whole system. Now the question is, will they be able to perfectly recognize the states, which one is given to them? Or in other words, can they be able to distinguish this set, this psi1 to psi(n) set? So the answer is actually always yes, when they are situated in the same lab. So they will perform a global measurement, and their measurement will be in this basis, psi1 to psi(n). As these states are orthogonal, this can be a valid measurement, and they will perform the whole measurement on this whole subsystem, and ultimately, just checking the outcome, they will know which particular state has been given to them. But let us consider another scenario, the second scenario. Alice and Bob are separated, spatially separated. They cannot perform the joint measurement or the global measurement now. But they are now allowed to perform LOCC, that is local operations and classical communication. So Alice can perform some operations on her local subsystem, and Bob can perform some local operations on his local subsystem. Additionally, they are allowed to communicate classically via you can say telephone. So in this particular scenario, will they be able to perfectly recognize the state, which particular state is given to them? Let us consider some examples. So here we have written a set of orthogonal 2-qubit product states, and you can see you can now consider that these set psi1 to psi-n is basically these 4 states. So referee will choose from this set one particular quantum state and will be shared among Alice and Bob. Now Alice and Bob's task is to perfectly recognize the state. So as I told earlier, Alice and Bob, when they are situated in the same lab, they can always perform a global measurement in this particular basis, as these 4 states are orthogonal states, and they can recognize the state which one is given to them. But when they are separated, then also they can perform a LOCC protocol, and they can perfectly know which particular quantum state is given to them. And this is basically first described in this PRL paper by Walgett-Hardy in 2002. So this set of states is globally distinguishable as well as locally distinguishable. Now let us move to another set. This set is basically the 2-qubit Bell states, 4 2-qubit Bell states. Now the question is whether they can globally it can be distinguished and locally it can be distinguished. These are the 2 questions. So globally it can be distinguished just by performing measurement in this particular basis. And when Alice and Bob are separated, whether there is an LOCC protocol which will distinguish these 4 states. Will they be able to perfectly recognize the state locally? The answer is locally, this set is indistinguishable. They cannot recognize locally by LOCC. This was a work by Shishir Ghosh and others. It is published in PRL in 2001. So this is basically a kind of quantum non-locality. Why? Because globally this task can be accomplished. This distinguishability task can be accomplished globally, but locally it is not possible. So that's why it is called quantum non-locality, and this quantum non-locality term has first been introduced by Bennett et al. And they have after that in a number of other literatures, this quantum non-locality in the framework of local indistinguishability has been used this term. So till now I am discussing with local indistinguishability only, but now I will move to a new quantum non-locality, which is local unmarkability, and it was a very recent paper. It was published in 2022 by Shamdat Sen and others. It was basically Dr. Manik Bonik's group. So based on these works, okay, after describing this work, I will come to our work. So what is the idea of local unmarkability? So here also the scenario is like that. There is a referee and 2 players, Alice and Bob. So the referee sends more than one state from a known locally indistinguishable set to Alice and Bob. So previously you can see that one particular quantum state has been sent to Alice and Bob. Now more than one state is there. So whenever more than one state is sent, then the question comes in which specific order the state is sent. So it should be sent in some order. And the task of Alice and Bob is to perfectly know the order by LOCC. So let me introduce the task just by some pictures. So let's say that the referee has these 4 Bell states, and when the task will be started, the referee will send all 4 Bell states to Alice and Bob, but in some particular order. So let's say that initially at the first run, the referee is sending B3 to Alice and Bob. So the number 1 state is basically B3, but Alice and Bob does not know the identity of the number 1 state. Secondly, the referee is sending B2. So B2 is the number 2 state. Thirdly, referee is sending B4. B4 is the number 3 state. Please keep in mind that Alice and Bob does not know which states are these. They need to know the order, in which specific order it is given. And lastly, the referee is sending the B1 and it is the number 4 state. So in how many ways these 4 states can be arranged? How many orders are possible? So there are only 4 factorial orders are possible, and I am depicting here one specific order. There can be other orders also. So now the task of Alice and Bob is to perfectly know the order of these states. Or in other words, you can say that they need to mark these 4 Bell states as number 1, number 2, number 3, number 4. Which one is which? Globally, it is very easy, because globally, when Alice and Bob will be in a same lab, they just will perform a Bell basis measurement on the number 1 state, on the number 2 state, another Bell basis measurement. In this way, they can easily know which state is which. They can easily mark the states, or they can easily know the order of the states. But when they are separated, when they are restricted to perform only LOCC, whatever be the order, it cannot be known by LOCC. That's why these 4 Bell states, these 4 2-qubit Bell states, are called locally unmarkable sets. It cannot be marked. Formally, this problem is denoted as NK marking problem. N means the cardinality of the set, that is, here we have 4 Bell states, that is n equal to 4 here, and K is the number of the states distributed among Alice and Bob. So all 4 states has been distributed among Alice and Bob, so K is also 4 here. That's why we are dealing with 4 Bell states marking problem. Now let us consider 4 3 Bell states marking problem. That means the original parent set is, the cardinality of the parent set is 4, and among these 4 states, 3 will be shared between Alice and Bob. Just like that, I have not shown in which particular order, but in some specific order. The task of Alice and Bob is to mark these 3 states. Globally, they can perform it very easily, perfectly, but locally, it is not possible for them to know the order perfectly. So 4 3 Bell states marking is also not possible. That is, local unmarkability is also present here. So here comes our question, based on which we have done our work. So it is basically an easier question than the question of marking. So we know that 4 3 Bell states are not markable, but can they be able to perfectly identify the identity of the 3 states given to them by LOCC? So now you can see this number 1, number 2, number 3, these numbers I have deleted. Why? Now the task is not to mark the states, but to know which specific 3 states are given to them. So how many 3 states can be given to them? 4 C3. So their task is now just to know which 3 states are given to them, not the order. So it is basically a easier question, because we need a lesser information. And this is our work that I have shown. So the title is Local Identification of Subsets of Quantum States, a Stronger Quantum Nonlocality. And as the task here is to know the identity of these states, we coined this task as local identification task, local subset identification task, because a specific subset is given to them and they need to identify which subset is given to them. So we have shown in our work that it is locally possible. By LOCC, they can identify which particular 3 states have been given to them, but they cannot know the order. That is, it is unmarkable. How they will know the which which 3 states are given to them? It is very easy. Alice will perform a JZ basis measurement on these 3 qubits, and Bob will perform another JZ basis measurement on these 3 qubits. And after that, the measurement results will be broadcasted or will be communicated among themselves via this classical communication, and they will tally the results, and then they can easily know which 3 states are given to them just by telling the outcomes of this measurement. And this is the JZ basis. That's why we call 4-3 Bell state identification problem. It can be solved perfectly, and this is a locally identifiable set. 4-3 Bell states are locally identified. So, just a small summary: 4-3 Bell states are unmarkable, but 4-3 Bell states are identifiable by LOCC. So the next question is there a set which cannot be perfectly identified by LOCC, but globally can be? That's why it will be a new kind of non-locality. So is there a set in NK identification problem? We keep it more general. And the answer is yes. So it is basically 4-2 Bell state identification problem. So from 4 Bell states, the referee will send 2 states to Alice and Bob, and the task of Alice and Bob is to know which specific 2 states have been given to them, but not the order. It is not the question of knowing the order, only the identity of these 2 states. And it has been shown that in our work, the identity of these 2 states can be known globally. It is very easy. They will perform just Bell basis measurements on each of these 2 states, but locally it is not possible. So there is again a mismatch here between the global scenario and local scenario, and so it is a new kind of quantum non-locality, and we coined it as local unidentifiability. You cannot even identify the states, let alone the order. So our claim is that local unidentifiability is a stronger quantum non-locality. Why is that? In case if a set is locally markable, it is obviously locally identifiable. If you can know the order of the states, you actually know the identity of these states. Otherwise, you cannot know the order. But the opposite is not always true. So, if a set is locally unmarkable, that does not mean that that particular set is also locally unidentifiable. So, the 2 examples what I have shown here are basically here. So 4-2 Bell is basically residing in this locally unidentifiable set, which is also locally unmarkable. But 4-3 Bell is a locally unmarkable set. However, it is locally identifiable. That's why we say that local unidentifiability is a stronger quantum non-locality. So now let me move to the application of local unidentifiability, and we have described in our paper the application in an application in secret password sharing. So the task is like that. Consider that there are 2 players, as I have shown, Alice and Bob, who are spatially separated and can communicate over phone, classically communicate over phone, and there is a referee. The target of this task is that a password in encoded form is to be distributed among Alice and Bob by the referee. The encoding should be such that as long as Alice and Bob does not come to a same lab, they cannot decode the password. So let me move to a scenario. Let us consider that A, B, C to Z, these alphabets are the constituting letters of a password, and each alphabet will be encoded to some quantum states which are orthogonal. It forms a set S, and this encoding is a common knowledge to all, Alice, Bob, referee. Now there is a password generator. Let us consider the password is Bengal. So for B, this particular quantum state will be chosen, just like that, B for E and for L. So this is now a password set. Now this particular S prime set will be shared among Alice and Bob. If Alice and Bob can perfectly know the order of this set, they will be able to know the password Bengal, because the quantum states are arranged in such a way that the order is just the same as Bengal, Bengal. So now let us consider that the encoding in a set of quantum state is, so that particular set is such that it is locally unmarkable but locally identifiable via LOCC. So what will happen? Alice and Bob cannot know which particular password has been shared among them when they are spatially separated, because they will not be perfectly know the order of these 6 states. But as this set is locally identifiable, this S prime set is locally unmarkable, but this S prime set is locally identifiable. As this S prime set is locally identifiable, that's why they can know these 6 states, these 6 letters. The constituting 6 states they can know. As a result, these 6 letters they can know, but they cannot know which particular order it is arranged. So A, B, E, G, L, N, they can know. So you can see, if this S prime set is, as this S prime set is locally unmarkable but locally identifiable also, the exact password is not known to them, but they can know the letters, constituting letters of this password, and as a result there is a finite probability that they can guess the original password. But what happens if this particular S prime set is a locally unidentifiable set? If it is a locally unidentifiable set, then they don't even know which 6 states are shared between them. It can be any from this S. So the identity of the letters of this password is not even known to them. The letters of this password are not locally decodable. So this is basically the task. The encoding should be such that as long as Alice and Bob does not come to a same lab, they cannot decode the password. So they cannot even know the letters. This basically gives enhanced security. Okay, let me move to the multi-party scenario. In multi-party scenario, we have also constructed the notion of unidentifiability. So these are the 8 GHZ states. Let us consider that 2 or more states are shared between them in specific by a referee. So we have shown that whenever Alice, Bob, and Charlie are spatially separated in 3 different places, these 2 among these 8 states are unidentifiable locally. But even if Charlie and Bob collaborate in the same lab, as a result, they can perform some global measurements on their subsystems, on their 2 subsystems. And Alice is in a spatially separated lab. As a result, Bob, Charlie, and Alice can communicate classically. Then also, 2 among these 8 states will remain unidentifiable. So it actually says that, and this phenomenon is basically part independent. in every party permutation, we have shown that local unidentifiability retains. That's why we coined this kind of quantum non-locality, local unidentifiability in multipartite scenario. This kind of phenomena is coined as genuine unidentifiability. And these example of genuine unidentifiability readily gives the example of genuine unmarkability also, which was open from the previous works. So let me come to the conclusion. We introduced a novel quantum non-locality, local unidentifiability, and this is a stronger kind of non-locality than its ancestors, like local unmarkability. It provides a tighter security in some password distribution tasks. We also extend it to multi-party scenario, and we come up with genuinely non-local version of local unidentifiability. That is, the multipartite set remains locally unidentifiable even in every bipartition. And we believe that this genuine unidentifiability may be of help in distributing secret information among networks and quantum internets. So that's all. If you have any question, please.
Thank you, Dr. Mukherjee, for your very nice talk. So I would like to request the participants to unmute themselves if they have any question.
I have one question.
Yes.
Thank you for your talk.
Thank you.
So if I understood correctly, password, to generate password, order is required.
Yes, let's say the password is Bengal. So if you type something else with the same letters, it will not work.
Yes. So question is, what about the Heisenberg uncertainty relation if we know exactly the order? So
in this case, you can see, so Heisenberg uncertainty principle is basically a feature of quantum systems, like two, like position and momentum, and there are some other things. But here the question is something different. Here you have the English alphabet. It is encoded in some quantum states. And now the question is, when the password is generated, whether you can know the order of this password, order of the letters of this password or not. So yes, when Alice and Bob are in the same lab, they can easily know the order of the password because they can perform some global basis data. So when they are spatially separated, they are not allowed, they are not able to know the password exactly. But when they are in the same lab, they can know. So it is not like a no-go thing, like the Heisenberg uncertainty principle. You can know when Alice and Bob are in global lab, in the same lab, they can know the exact password. I think.
So does it mean that you are classical through the classical communication, right? Or if you are doing quantum, then
if you are doing quantum communication, if you are allowed to send these quantum states to Bob, then yes, Bob will know which particular password is here. But as this, the operation what Alice and Bob can perform is restricted to LOCC only, local operation and classical communication only. They are not allowed.
Thank you.
Okay, so if there are no further questions, let us thank Dr. Mukherjee for his very nice talk.
Thank you also the organizers for arranging this kind of conference. Okay, shall I stop my sharing?
Please. Thanks a lot.
Yeah, I can hear you. So could you please make me co-host?